All right. All right, I think we're good to go now. All right. So when we have zero slope, of course the derivative will have an x-intercept. When we have positive slope, we'll have a positive y-coordinate. In our derivative, with negative slope, we'll have a negative y-coordinate. And then we have two weird cases. If your original function has an asymptote, in other words, a vertical asymptote is in the graph somewhere, we will have an undefined derivative there as well. And if we have a cusp, also called a corner or a peak, a sharp turn in the graph, yes. What's that? Oh, yeah, you were absent. What is n? Oh, what is a derivative? A derivative is the slope of the curve at any point, right? So we use this formula to find the derivative. Okay. So we could have a cusp or a corner. In that case, we'll have a discontinuity. Now, I don't know if you put 2 and 2 together with this list, but what this really means is that the domain of the derivative could be a little bit smaller than the domain of the original function because of that last category. At a corner or a cusp of a graph, like the absolute value function, we do have our function defined there. We even have a limit there, and it's even continuous there. But there will be no derivative there. It's impossible to draw a tangent line on that peak. Or I should say there's an infinite number of possibilities there. Now, we did go through some of these graphs yesterday, so I'm not going to go through them again. But I am going to take a look at some of the new ones. All right, so let's go to example 2, which we did not get to. That's sort of where we left off yesterday. But we want to make sure that we understand the principles. When you draw or sketch the graph of the derivative, you should be thinking slope. Remember, the derivative is the slope. So you should be thinking about slope when you look at the original function. If you are thinking about slope, you should be able to draw the graph of the derivative here very easily. Look at what you have here. You have constant positive slope. What's that going to look like on our derivative graph? Like this. We're going to have a horizontal line with a positive y-coordinate in our derivative graph. Why is it horizontal? Because the slope didn't change. Like, let's say your slope was, I don't know, positive 1 here. You will have a horizontal line through 1 on the y-axis. Now notice I've got an open circle here. That's because I have a peak right there, a cusp. And this means we won't have a derivative right there. So what does that mean? We're going to suddenly switch to negative slope. But it's a little bit more negative than it used to be positive. Yes? Well, here our slope, let's say the slope is exactly equal to 1 all along this part of the curve. So remember, the graph I want to draw here is the graph of the slope, right? So from this point straight to negative infinity, I need to have a graph at 1, exactly at the y-coordinate of 1. The y-coordinate must match your slope. So if your slope is 1, the y-coordinate of the derivative is 1. Okay, suppose the slope here was, I don't know, let's say -2. How would you draw that? Well, here's the positive y's, here's the negative y's. So we would have, whoops, we would have a horizontal line down here, starting at whatever point this is. Let's say that's A. And we'd have an open circle with a negative y-coordinate down there. All right, so positive y-coordinate, let's say at 1. Negative y-coordinate, let's say at -2. All right, I hope you're picking up the concept here. We're looking at the slope. Now take a look at graph B. First of all, we have an asymptote right here. So I don't know, let's call that point B. So also at point B on our derivative graph will be another asymptote. So wherever the original graph is undefined, the derivative is also undefined. How can you do a slope when there's no y-coordinate? All right, look at the left arm of the graph. Here our slope is positive, but not very much positive. It's a small positive value, but as I go to the right, what happens to the slope? Increases towards infinity, doesn't it? So starting almost at 0, increasing to infinity, the derivative graph will look much like the original graph here. There are some functions that have identical graphs to their derivatives. Actually, one in particular. The graph of y equals e to the x has exactly the same derivative graph as the original graph. And so that can happen. This is a very famous function for that. And it's named after the person that invented it, a German mathematician by the name of Leonhard Euler. E-U-L-E-R. Okay. Now take a look at the right arm of the graph. What do you notice? Very steep negative slope, getting less negative, and getting less negative, and even less negative, but still negative. So the derivative arm would actually be down here. We have to have negative y-coordinates for the right arm of the graph, not positive y-coordinates. And we want the y-coordinates to be quite negative at first and get less and less negative as we go, going towards 0, right? So as our slope goes towards 0, so the graph goes towards the x-axis. All right. Okay, we got some more graphs to do here. All right, class, I'm going to let you try question C. If you've been listening to me, I'm hoping that you'll be able to do this one. What I suggest is maybe write an actual slope for each part of the graph. Like make an estimate of what you think the slope is. And then down below, make yourself a little y and x-axis. And down below, write the derivative graph. Remember, the derivative graph has to reflect what the slope is doing. So what would it look like? All right, suppose your slope was -1 here. Here we look horizontal, so it looks like our slope is 0, right? Is there any point on the original graph that you think we won't have a derivative? Yeah, at the corner. We never have a derivative on a sharp corner like that. All right, so I'm not sure what point that is. It doesn't say, but we're going to have that same point right here on our derivative graph. Okay, so what I hope you did is I hope you did a horizontal line at -1 with an open circle like that. representing this arm of the graph. After that, I hope you did an open circle and did a horizontal line right on the x-axis, excuse me. Did anybody have that? Some of you did. Good for you. All right, so you're getting the idea. Let's take a look at D. All right, so we've got two cusp points here. Let's call them A and B. So our derivative graph will have undefined points, a hole in our derivative graph on those 2 points. Now I'm going to sketch my derivative graph in green, purple. All right, so what do I have? 0 slope, then maybe -1 slope, and then back to 0 slope. How could I draw that? Well, I need a horizontal line until I hit A. I need an open circle right there. Then I need a horizontal line at -1, open circle here, until I hit B right here. Then at B, I'll bounce back to the axis, and the rest of my graph will be there. So I go from a slope of 0 to a slope of -1, back to 0. Did anybody have that? Good for you. All right. Question G is much like the one we did first of all in example 1. Can anybody take a guess at the degree of the polynomial graphed in G? It's probably a degree 4. It's got 4 x-intercepts. It also has 3 turning points. So the degree is usually 1 more than how many turning points we have. So we have 3 turning points. This is degree 4. We talked earlier about this. When you do the derivative of a degree 4, the graph becomes a degree 3. Isn't that interesting? You lose a degree. Okay, I'm going to use blue on this one. Keep in mind that whenever our slope is 0, like here, here, and here, those are key points for your derivative graph. What do they represent on your derivative graph? What does 0 slope represent on your derivative graph? X-intercepts. So we're going to have an x-intercept here, and here, and over here, it looks like. And then our graph will alternate between positive and negative and positive slope. So negative slope, positive slope, negative slope, positive slope. So we need to be below the x-axis, then above, then below, then above. And look at that perfect cubic shape that we just drew. So the graph, the derivative of a quartic appears to be a cubic. Question H would be a challenge question. Okay, they're not all going to be this difficult. Question H is certainly going to make sure you know your stuff here. All right. We seem to have 2 asymptotes, let's say at A and B. So at A and B, our derivative graph will share the same asymptotes. So the domain of the derivative graph could be the same as the original graph, but it can never be more generous or wider than the original graph. It might be a bit more narrow, especially if you have cusps and corners and peaks. Okay, what about this section of the curve? Negative slope, getting more negative. That will be exactly the same on the derivative graph. So here, our y-coordinate will be quite close to 0 because our slope is close to 0. Here, our slope is really negative and so our y-coordinate becomes more negative. However, for this one, we have positive slope over here, don't we? So actually, the derivative curve will be reflected upwards, like that. So in some cases, the derivative curve looks like the original function. In other cases, not. And we've got both cases on the two halves of this section of the graph here. So with the right-hand case, we have positive slopes, right? That'll be reflected with positive y-coordinates. But here, negative slope, so we end up with going in that direction. Oh, we did have one x-intercept because we have horizontal slope right there. We do have x-intercept right there. Okay, and this monster lesson is almost done except for the definition of differentiability, a big word. What is differentiability? Well, we say that a function is differentiable big word. It's differentiable at x equals a only if the derivative exists there. I mean, that's pretty obvious. So if f prime of a exists at a, it's differentiable at a. Here it is in layman's language, okay? This is the official mathematical one, and this is a description. You must be able to find the slope at x equals a. If you can't, it's not differentiable here. Now, there's some obvious reasons why you couldn't find the slope. Either there was no y-coordinate, no x and y coordinate there for the original function, or you had a peak or a corner where it makes it impossible to draw a single tangent. Okay, so to be differentiable, f of x must be continuous at this location. Also, a function is never differentiable at a vertical asymptote. I hate that when I do that. And it's also never differentiable at a corner, or if you like, a cusp. It's called different names in different books. I've even seen a book use the word kink. That's sort of kinky. All right, so corner, cusp, or a kink. Whatever you want to call something like that, okay? That's what, I mean, there's different names in different textbooks. An abrupt change in the graph, right? Which can often happen when we're doing separate definitions, like piecewise definition for our graph. Okay. Okay, so where is this function differentiable and where is it not? Okay, so this one is not differentiable. At x equals -3 and x equals +2. So there are two problems here. We have asymptotal behavior at -3, and we have a cusp at +2. All right, so let's take a look at the last one here. Can you list all the points that you think there's no derivative, please? So for this example, please list all the points that you think there would be no derivative possible. So this is your original function. This is not the graph of the derivative. This is the graph of the original function. So where would we fail to have a derivative? I hope you can all see that A is okay, right? B is good? How about C? No. How about E? D? F? No. And even not G. Now, we're going to test you your knowledge of last unit. Why is there no limit at G? Yeah, we got a left-hand limit, but no right-hand limit. So remember, to be differentiable, you have to have the limit. It has to be continuous. And if it's continuous, it must have the limit. In other words, how could you draw the tangent line here? Let's be honest. There's a zillion solutions. You could draw the tangent line like this, like this. Same thing up here. Like, whenever you can have multiple tangent lines, you're not differentiable. So we are not differentiable at x equals C, E, F, or G. And I've got some good news. The monster lesson is over. So from this lesson, from our first lesson, what do I expect? I expect you to know how to use that formula to find the derivative by first principles. I'm going to do one more of those. One more of those today when we get to the appropriate place in lesson 2. All right? After that, we're going to say goodbye to first principles and develop some super shortcuts known as the product rule, the power rule, and the sum and difference rules. And you're going to love them. Okay. You're going to love them. All right, so which one? I think I'll do that one. Okay. Could you turn to section 2.2, 2.3, and don't be concerned about the fact that there's 2 textbook sections represented here. We are going to cut through this like a hot knife through butter. All right? Okay. All right. Could we quickly, we're going to begin with a very simple function, y equals 3. If I drew y equals 3, what would it look like? A horizontal line through 3 on the y-axis. Do we agree? I think it's pretty obvious from this trivial graph that its slope is always 0. You'd be okay with that, right? So here's what we can write. We can write that the derivative of any constant function is 0. The derivative of any constant function is 0. So the derivative of 3 is 0. And its slope will be 0. Okay, let's go to the derivative of y equals x. We're going to try to look for a pattern here, okay, folks? So that we can develop a formula. What does y equals x look like? Goes through the origin. Its slope is 1. And that's a pretty good clue. The derivative of x will be 1. A very important foundation stone. The derivative of the variable x is always 1. So, we're losing a degree, aren't we? X is degree 1. Its derivative is degree 0. A constant function is degree 0. It doesn't matter which variable you use, like the derivative of u, the derivative of z, the derivative of t. Whatever you use, they're all going to be equal to 1. But perhaps the most important rule that we're going to study today is called the power rule. What is the derivative of x to the n power? Well, if you missed yesterday's class on doing things by first principles, can you watch this one more time? I've got the formula up here, right? So if f of x equals x squared, what would I write? I would write f prime of x equals limit. Oh, this isn't going on here. Sorry. I keep forgetting. Okay, so if f of x equals x squared, then we have f prime of x equals limit. H goes to 0. X plus h squared minus x squared over h. Could you write that in your notes right there? We're going to simplify it. We're going to simplify it. Up top, what would I get? Do you know how to square a binomial? Huh? Do you? Okay. So x squared plus 2xh plus h squared minus x squared over h. What's going to cancel in that numerator? X squared. Will the h divide into the remaining terms? Yes. So h divides in here, giving us 2x plus h. But we're allowing h to go to 0, aren't we? So doing it by substitution, our derivative of x squared is what? 2x. Okay. We're going to do one more. One more. And I am out of space here. So we'll just put it over on the side. Yeah, I can do that. Okay. Y equals x cubed. We're trying to notice a pattern. You think it's going to be 3x squared? Well, we got to find out. Limit as h goes to 0, x plus h quantity cubed minus x cubed over h. Okay, so on the top, I can clearly hear the expression telling me to do something. Oh, you don't hear the voice? It's just me? Oh, sorry. All right. This is a difference of cubes, isn't it? And haven't we studied difference of cube factoring? Oh, yes, we have. Whether we wanted to study it or not, we did it. So what is it? X plus h minus x. And in here, what? X plus h squared. Let's get rid of this line. It's too confining. Plus, then the product of the two of them. And then finally, the last one squared. And there we have it. We've factored our sum of cubes. Okay, now watch. If you don't watch closely, you're going to miss it. Are you ready? Here I go. I'm going to do something bold. Legitimate or not? Yes. Legitimate. Yes. 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 And remember when I said when you get rid of the h, you're home free? We're home free now. We can do it by substitution now. It's a determinate limit. I can let my little h go to 0. X squared plus x squared plus x squared. If you guessed 3x squared, you were absolutely right. All right, so let's just do a little bit of if y was x, or x to the first power, y prime was 1. If y was x squared, y prime was 2x. If y was x cubed, y prime was 3x squared. If y is xn, y prime will be n x to the n minus 1, and a new formula is born. I can now do the derivative of y to the 6th, y equals x to the 6th power with my eyes closed. Okay, I have to open my eyes. Done. Just like that. So whatever your exponent is, comes down as a multiplier in front, and the power is reduced by 1. So if it's x to the 6th, it'll be 6x to the 5th. Exactly. Yeah.
So if we have a discrete thing where it's like x to the 6 plus x to the 4 plus x to the 3, we just do it for every individual.
Yes, that's all coming up in today's lesson. But that's good for foreshadowing. All right. Foreshadowing. In this box right here, can you write n, x to the n minus 1? Very clearly in there, please. I'm going to answer your questions because you guys are actually, you are leading right into my examples. Because that's exactly what we're going to do here. Example 1 is, what if you didn't have x squared? What if you had 3x squared? What would you get? If you write it like this, you'll be able to understand what I'm doing. Y prime, our derivative then, will be 3 times the derivative of x squared. We already said that one is 2x. So y prime equals 6x. And if you go back to example 3 of our previous lesson, I don't know why it says example 1, or was it example 1? Yeah, it was example 1 in the previous lesson. You'll find that we did it by first principles. We used the formula, and we got 6x in the end, didn't we? So here, using the shortcut, we get the same answer. All right, class, suppose I'm dealing with x to the 4th power. What would be the derivative? What would be the derivative for x to the 4th power? 4x cubed. So get used to this. We're going to take a look at some of the applications that you can have here. Okay. All right, just before we go on, there's a couple more I'm going to throw in free of charge. I don't know where you're going to write them. Okay. The nice thing about the power rule is it works for any power, even fractional powers. Yes. Another way of writing x to the root x is x to the half power. Write down in the next step what you think the derivative of x to the half power would be. I'm sorry. I just felt that these should be in your lesson, even though they're not there. Okay? What is the derivative of x to the half power? Bring the half down in front, And then for the power, reduce it by 1 unit. So what's 1/2 minus 1? -1/2. And that turns out to be the correct derivative. Whoa. Next one. Shh. You try this one. What is the derivative of of x to the -2 power? What would that one be? -2x to the -3, exactly. Okay, now I think we're ready for the next page. All right. Could you now do the derivative of x to the 100th power? And then next to that, do the derivative of 5x to the -3. What would the derivative of 5 times x to the -3 be? If the original function is expressed as f of x, we usually write the answer as f prime of x. But it wouldn't be wrong to use y prime. How many had that answer for number 1? Good job. Okay, number 2. You can do it in 2 steps if you want. You can write the 5, and then in the bracket write what the derivative of x to the -3 is. Sorry, put the 5. Oh, sorry, why did I put a -1 there? It's an f, sorry. F prime is what I meant to write. Okay, so it's going to be 5 times the derivative of x to the -3. There's your derivative, -15 over x to the 4th. Okay, number 3. At what point on the curve 3x squared is the slope of the tangent 24? Now class, last unit, you would have been playing around with a formula like that, right? Watch how fast you can do them now. Watch this. All you have to do is find your slope by taking the derivative. The derivative would be 3 times 2x. Our derivative is 6x. All you have to do now is take the 6x, set it equal to the desired slope, and solve for x. Now, if I was marking this and I was the student, no, I can't be the student and the teacher at the same time. But if I was marking this and the student showed me this, I give them like 1.5 out of 2. Why? What am I missing? I did find the x coordinate. What was I asked to find? Can you remember that somehow? I'm not sure, but the y coordinate the y coordinate is simply found by putting the 4 in for x in the original function. If you got a y coordinate of 48, you're right. So our original point is 4, 48. That's the point of tangency. All right, give yourself a pat on the back. You're halfway through the lesson. Okay. All right. All right. Now keep in mind that finding a derivative is equivalent to finding a limit. A derivative is a special limit. This one right here. Shh. Okay, need everybody focusing. Your undivided yet multiplied attention right here. A derivative is a type of limit. So it makes sense that it obeys the limit laws you learned last unit. So what that means is if you take the derivative of a constant times a function, taking the derivative distributes over this, and we are glad it does. So the derivative of a constant times a function is the constant times the derivative. Very nice. You'll also be happy to know that taking the derivative over a sum and a product, a sum and a difference, also distributes. So if you have a sum or a difference, you can take the derivative of f of x and take the derivative of g of x separately and just add or subtract the results. So whatever limit laws you learned last unit apply here. They obey the limit laws. I gave you the good news first, so now I'm going to give you the bad news. Unfortunately, taking the derivative does not distribute over a product or a quotient. It would be so nice if it did, but that's a future lesson. That's next week. Yes, we do have rules to do it, but it's not straight distribution like this. All right, so what do I mean by distribution? I'm going to do this first example for you. Okay. We can see here that in this polynomial, we have a couple of variables, but also some constants being multiplied, and then we have three terms. Our derivative now will distribute over all three terms. So we'll first of all take the derivative of 2x to the fourth. That would be 2 times the derivative of x to the fourth, which is 4x cubed, minus 7 times the derivative of x, plus the derivative of 5. 5 is a constant, so its derivative is 0. And some of you are probably wondering, Mr. Ashton, could we do that step in our heads and just go straight to that? Well, you know what? Your teacher's coming back a week from Monday. All right, so I won't be here for your next test, so do what you want. No. So I think I would allow that. This one's pretty easy to go straight to that step. But especially when you're first starting, you might want to put the intermediate step. Okay? So derivative of x to the fourth, 4x cubed, multiply that by 2. Derivative of x, right there. Okay, I'll give you some advice, though, for number 2. Look what I'm doing. If they give you a function in radical form, do yourself a favor. Change it to exponent form to begin with. Our power rule is set up for exponents, not radicals. So if you write it like this, then you should be able to do the derivative fairly easily. Can you do that derivative for me now? By the way, they say it is that if you take something away, it's good manners to put it back where you found it. And so it is with these derivative questions. If the original function is in radicals, it is traditional to give our final answer back as a radical, because that's how they gave the question. Right? So we can do the derivative using the exponents. Right? So f prime of x would be half x to the negative half plus 1/3 x to the negative 2/3 plus 1/4 x to the negative 3/4. How could we write this in radical form? This one would be 1 over 2 radical x, square root x. This one would be 1 over 3. And now the 2/3 power, you could write that in two different ways. One way is the cube root of x squared like that, with the square inside the radical. You can also put it outside the radical and use a bracket. And it's the same thing with our last one. A little less writing to write it that way. Okay. Now, if you take a look at question 3, this is a product. We have not used the product rule, and we will not use it in...
Jordan Kwan and Factory Taker, please come to the office. Jordan Kwan, Taker, please come to the office.
And we will not use the product rule till next week. So for now, until we take that rule, we will FOIL this out. Did I FOIL correctly? Check my work. 3t plus 2 multiplied by 2t minus 1. Did I get all the products right? Okay. Which two terms can be combined? Middle. Now do the derivative for me. Okay, now that we've multiplied it all out, and it's now sums and differences, get me the derivative. How many like my answer? Do you like it? Okay. It is correct, isn't it? Notice the derivative of negative 2 was 0. I didn't include it. So I did the derivative of 6t squared. I did the t squared as 2t multiplied by 6 gave me 12t. The derivative of t is just 1, just like the derivative of x is 1. And then the derivative of negative 2 was 0. Okay. We have two more questions, but they're a little bit lengthy. It's okay, we have 20 minutes or so. All right. At what points on the curve y equals x cubed plus 3x squared minus 24x plus 1 have a horizontal tangent? Okay, what does that mean? What is the implication of having a horizontal? Yes. That's right. So remember, the derivative is slope, right? It's the slope of a curve at any point. So what I want to do, my strategy, listen to my strategy. Listen to my no, okay. All right. My strategy, is to take the derivative and yes, set it equal to 0 and solve for x. This is a very common strategy, and it's used quite often in maximum and minimum word problems, which are coming down the line in this course. Do you know why? Because most maximums and minimums occur where the slope is 0. So this procedure that you're about to do is extremely important. All right, so let's watch it. Okay, now, at what points on this curve do we have a horizontal tangent? Here's my strategy. I'm going to find y prime. I'm going to set it equal to 0, and I'm going to solve for x. Well, you can call me a dreamer if you want to, but my confidence in this group is growing, especially after the results of the last test. I'm thinking you guys can do this one. That's my strategy. I want to take my derivative of this. I want to set it equal to 0. Oh, you're going to make us factor a cubic equation, Mr. Ashton? No, I'm not. Yes, this is cubic, but when you take its derivative, it'll be, agree what? 2. So I'm not making you factor a cubic here. Yeah, I'm making you factor a quadratic. Okay? Go for it. You should either be working or your hand should be up asking for help. Not your hand asking, but if your hand is up, you can be. Okay. And there's a way to shut this down. Okay, let's take a look at your progress so far. All right. What's the derivative look like? 3x squared, 6x minus 24 plus 0. We set it equal to 0. We divide both sides by 3, or we factor out a 3. Either way. We factor the resulting trinomial. X, 4, 2, plus, minus. We end up with 2 solutions. And I'm done, right? Oh, they asked for the points. They asked for the points. I need my y coordinates. Anybody find the y coordinates? You substitute into the original, so we're not going to waste time with this. It's pretty straightforward. You just put it in the original equation. Don't put them in the derivative. This gets substituted in the original equation to find the y coordinate. Okay, this is what I got. I got negative 27 when x was 2, and I got positive 81 when x was negative 4. Okay, we have one last question. In question 5, we're going to be a little bit more mysterious with you. Okay? Yes, mysterious. You know, when I was your age, I had thick hair like you.
My grandpa had
But not it won't necessarily happen to you, okay? It's not, okay. I'm just so jealous. I can hardly handle it. Like, you can do that peak thing and everything. I can't do that. All right. I mean, I guess I could, but it'd be more like a tunnel. All right. All right. Okay. What is the mystery of question 5?
How do you do it?
There's a missing coefficient, people.
Yeah.
There's a missing coefficient. And you would have no hope of finding that unless you had a clue. But what if you don't have a clue? That's not you. All right, so there's the clue. They've told you something about it. They told you, okay, wait. Shh. I know it's been a long class. We're almost home, okay? We're almost there. All right. If I take the derivative and substitute -1 in the derivative and set that equal to -6, I bet you I'll create an equation where I can find what A is. Okay, first of all, the derivative. Did I do the derivative correctly? Everybody, take a quick look at my derivative. Is it right? Okay, so what I want to do now is put a -1 wherever I see x. And I want to do one more thing. I want to set it equal to what? No, not 0. -6. What? What have I created? A monster? No. An equation to solve for A. Question, yes? Okay, remember, we're substituting this into the derivative, into here. Okay? And when we do the derivative, there's not an x there anymore to turn it negative. Okay? Could everybody solve this for A, please? I'll give you a hint. A should be negative. A negative number between -20 and -25 in there. Did you say -22? That's what I got. Okay. Okay, so this is 6. Yes. All right, so I hope you enjoyed the element of mystery in 5A. And now in 5B, we have even more mystery. 2 missing coefficients. 2 of them. Well, class, they have to play fair with you. If they give you 2 missing coefficients, they better give you 2 hints. And they do. They give you the derivative at 1 is 15, but they also say that the derivative at -1 is +23. How many are getting that 2 equations with 2 unknowns feeling?
I am.
Yes. All right. 2 unknowns, 2 equations. So f prime of x, 4x cubed, 3ax squared, 2bx minus 2. That's f prime. Now we're going to substitute 1 in f prime. So it'll be 4 times 1 cubed plus 3a times 1 squared plus 2b times 1 minus 2. And we're going to set that equal to 15. So this is 4 plus 3a plus 2b minus 2 equals 15. That means 3a plus 2b would be equal to 15 minus 2. Uh-oh, we got an unlucky number, 13. Okay. Now, class, I don't want to steal all the fun here. So could you get me the other equation? Take your derivative and substitute -1 and set it equal to 23. And I promise you, this is the last thing I'll make you do today. That's it. This is it. This is the end of the lesson. right? I promise you. Oh, you want to do another one? You mean after this one? I don't have any more tricks in my bag. Oh, I could do one from the homework, maybe. No? Okay. Okay, so for this one, what I got when I simplified it was 3a minus 2b equals 29. Now, let's put a box around these two equations. How many feel like adding those two equations? You feel like adding them? How many feel like subtracting them? Okay, so you can do either one, right? Both of them will work. You can either add them or subtract them. Let's write them underneath each other. I don't know what you want to do, but I want to add them. I get 6a, and the b's are gone, and I get 42. I discovered that my a value must have been 7. And how do I get b now? Sub it back in. Let's pick the lucky equation with 13. All right, so 3 times 7 plus 2b equals 13. 21 plus 2b equals 13. 2b equals negative 8. It's a really sloppy 8. Whoever's listening online, I apologize for that 8. Okay, so b equals negative 4. All right. And there is homework. There are 2 parts from your homework now. All right, there's the 2.1 assignments where you're doing the graphing thing. And then this homework assignment here. All right, I'm signing off now. So if you're listening online, that's the end of it. Okay.